Welcome to Equilibrium Electrochemistry. Alright, so far we've discussed general cases and our conclusions have been applicable to all reactions. But now we want to examine the reactions that take place in electrochemical cells. So, the ability to precisely measure differences in electrical potential, so voltage differences here, means that we can use electrochemical methods to determine thermodynamic properties of reactions that may be difficult to determine using other methods. So if we can't do measure, say, Gibbs energy via thermodynamic means, by calorimetry, maybe we can use electrochemistry and a voltaic cell to probe the thermochemistry that's going on here. So remember that an electrochemical cell is composed of two different electrodes. They're usually metallic conductors, although sometimes graphite is used. And these electrodes are in contact with an electrolyte, so some ionic conductor, which is, again, generally a solution, or a liquid or solid. An electrode and the electrolyte it's in contact with will comprise an electrode compartment. So this may be a half cell, or it may not be. So note that our two electrodes can share the same electrode compartment. In general, we try to keep them separated, but sometimes they'll be in the same compartment. So if our two electrolytes are different, then they'll generally be connected together using a salt bridge. Remember, we need to have a complete circuit, so we need to have charges flowing through maybe an external circuit, and from an electrode into the electrolyte solution, from one electrolyte solution to the other, probably across a salt bridge, where we allow some positively charged cations and or some negatively charged anions across the salt bridge. They're usually the counter-ion to whichever ion is undergoing oxidation or reduction. And so a galvanic cell is an electrochemical cell in which electricity is produced by a spontaneous chemical reaction that occurs inside of it. An electrolytic cell is an electrochemical cell in which electricity is necessary to drive some non-spontaneous chemical reaction that occurs inside of it. So basically, if we have a galvanic cell, if we want to go the opposite direction, so charging it up, recharging a battery, we're now calling it an electrolytic cell. We're basically going the opposite direction. We're doing work on the cell, we're putting in some energy via work, and we're getting the non-spontaneous reaction to occur instead of the spontaneous reaction that thermodynamics predicts. So remember that oxidation is the removing of electrons from some chemical species, and the production is the addition of electrons to some chemical species. And the combination of these occurs in a redox reaction or an oxidation-reduction reaction. I'm going to use the term redox. So the species that donates the electrons is the reducing agent or the reductant. Note that in the process of reducing the other species, the reducing agent itself gets oxidized, because in order to reduce something else, that other thing needs to be gaining electrons, which means the reducing agent needs to be losing electrons, so it's being oxidized. And then, on the other hand, the species that accepts the electrons is the oxidizing agent, and in oxidizing the other species, the reducing agent, the oxidizing agent is reduced, because in order to oxidize something, you need to remove electrons from it. In order to remove electrons from something else, I need to gain electrons, which means my charge is getting more negative. So I'm being reduced. So we can write a redox reaction as the combination of two half reactions. We can split this, our electrochemical cell, into two half cells. So two half reactions. Note that often we're expressing the redox reaction as the difference between two reduction half reactions. Not as the addition of an oxidation and a reduction reaction. Note that a reduction reaction is simply the opposite of an oxidation reaction. If we have some oxidation reaction and we flip it around, well, instead of removing electrons in the oxidation process, well, now we're adding electrons for our reduction process. So we just flip the electrochemical reaction around to go from the oxidation to the reduction, or reduction to oxidation. And now we're flipping the voltage difference that we have there. So the reduced and oxidized species in a half reaction form a redox couple, and we can write our redox couple as oxidation slash reduction, so ox slash red, where our reduction half reaction looks like this. So we have our oxidized species plus some number, V here, that's our stoichiometric coefficient. Some number of electrons gives us our reduced species. So over on the right side here, you can see we have an electrochemical cell. So we have oxidation occurring here at the anode. We have reduction occurring at the cathode. The anode has a negative charge, like anion. The cathode has a positive charge, like cation. And our electrons are flowing from the negative side to the positive side. Remember, our electrons will be repelled from a negative charge, so they're going to tend to want to move away from the anode, and they'll move through the circuit. Usually we have some kind of load up here, and the electrons will be attracted to the positive charge, so the cathode, and then the electrons go in and they then go into the species that is being reduced. So we start out with our oxidized species in our electrolyte. We add some electrons, we're adding electrons here, and we end up with a reduced species. Right? So that's occurring on the right side here. So we can often express the composition of an electrode compartment in terms of the reaction quotient Q of our half reaction. So in the expression that we have for Q, we ignore the electrons. We're not interested in what the electrons are doing at this point, not for Q. Because we don't have, remember Q is involving the concentrations of our reactants and products. We don't really have a concentration of electrons. So we typically separate the oxidation and reduction processes in space so that we have a flow of electrons through an external circuit, like what was shown on the last slide, so that we can do some work. If we have both of them occurring in the same place, in the same beaker, then we can't extract any of that energy to use as work. And we'll basically just get it out and get lots of energy out as heat. Which is great if we want heat, if we're cold, if it's the wintertime, but if we want to be able to turn on the lights or recharge a battery, we want to be able to get that energy out. So oxidation occurs at the anode, and reduction occurs at the cathode. And in a galvanic cell, the cathode has a higher electrical potential than the anode does. Right? The cathode is more positively charged than the anode, which is more negatively charged in comparison to the cathode. So the species undergoing reduction at the cathode withdraws electrons from the cathode, causing a relative positive charge to occur on the cathode. And the species undergoing oxidation at the anode deposits electrons on the anode, causing the anode to become negatively charged. And an electrochemical cell, which is not at equilibrium, can do electrical work as the overall cell reaction drives electrons through an external circuit. If we've reached equilibrium, well, now the electrons aren't flowing anywhere, in which case we can't do any work. And at that point, we call the cell dead. So the work that can be accomplished depends upon the electrical potential difference between our two electrodes. So the voltage drop, basically, from the cathode to the anode. So the larger the potential difference, the larger that voltage drop, the greater the amount of energy transferred with each electron. So each electron carries more energy if that potential difference is larger. This is essentially the same thing as having a molecule of water fall down a waterfall. The higher the waterfall is, the greater the potential difference, the harder that molecule hits at the bottom of the waterfall. The taller the waterfall is, the harder, the greater the force is, and thus, if we put a water wheel in there, the more work we can get out of that water as it's falling. So a cell at equilibrium has a potential difference of 0. If the potential difference is 0, then we can get 0 work out, which for us generally means it's a dead cell, it's not useful to us, and we throw it out or recycle it. Don't throw batteries away. So remember that the maximum non-expansion work that can be done by a system is W at max. So this is the additional work, so non-PV work is what we're talking about here. This is the maximum amount of non-PV work we can do is equal to delta G. So the change in Gibbs energy. So if we assume that all non-expansion work is electrical work, so we have no other kinds of work going on, then the additional work is equal to, or the maximum additional work is equal to WE, where SWE is the maximum amount of electrical work we can do. So, remember that the maximum work is produced when the system, or electrochemical cell in this case is our system, when the system changes reversibly. So in order to draw thermodynamic conclusions from the measurements of work that an electrochemical cell does, we have to ensure that our cell is operating reversibly. So also remember that the reaction gives energy is a property relating to a specified composition of our reaction mixture. So, in order to use our Gibbs energy of reaction, delta RG, we have to be sure that our cell is operating reversibly at a specific constant composition. Because remember, as we change the composition, our delta RG is going to change. Because now we're changing the composition, so we're changing the Gibbs energy involved in the mixing, changing the entropy involved here. So, we can ensure these sorts of conditions if we measure the cell potential when it's balanced by an exactly opposing source of potential. So if we have an electrochemical cell and we hook up a circuit to it, but on that circuit we put in a voltage difference that exactly matches. And so basically what we do is we take a power source, we hook it up to our electrochemical cell, and we change the voltage of our power source until the voltage difference is such that electrons aren't flowing through the cell or the circuit. And at that point, now we can tell what our electrochemical potential is. So in this case, now our cell reaction occurs reversibly because the composition is constant. We're not really allowing electrons to flow one direction or the other, and no current flows. So, the resulting potential difference is called the cell potential, so E cell. Right? So E there stands for electromotive force. So this is basically a voltage. We measure this in volts. So that's our cell potential, E cell. And so in the book, it can then be shown that the relation between our reaction gives energy, delta RG, and the cell potential looks like this. So we have minus V, where V is the number of electrons that are being exchanged in the reaction. Okay? That's our stoichiometric coefficient of electrons in our half reaction, or in our half reactions. And so we've got minus V F E cell. So E cell again is the potential difference of our cell, the electrical chemical potential difference, and F is Faraday's constant. So note that F, Faraday's constant, is equal to E, the charge on each electron, times Avogadro's number. So this is 1 mole's worth of electrons, the charge on 1 mole's worth of electrons. That's called 1 Faraday. So, by knowing delta RG at a specific composition, we can then state the cell potential at that composition. Because if we know this value, and we're assuming here that we know what chemical reaction we have going on, so we know the value for V, and we know what the value for F is, because that's a constant. So, if we know delta RG, then we know E cell. So, now we can interpret that equation as showing that the driving power of an electrochemical cell is proportional to the slope of the Gibbs energy with respect to the extent of reaction. Okay, so as we have our chemical reaction go, we have some slope of Gibbs energy with respect to that extent of reaction, and now we're relating that slope, at delta RG, with the driving power of our electrochemical cell. So remember, we've got a graph that looks something like this. As we have our reaction go, we've got some slope, and the slope gradually decreases until we reach equilibrium here. And so the reaction proceeds until the slope here is 0. So note here that we have our Gibbs energy as a function of our extent of reaction xi. And on the right side of this minimum, then the reaction is spontaneous to the left. On the left side, the reaction is spontaneous to the right. At that minimum, the reaction occurs reversibly, which means that at that point, we're at equilibrium. Right? Once we've reached that point, we're at equilibrium. Both the forward and reverse reactions occur simultaneously, and the rates are equal to each other. So, and a reaction that's far from equilibrium has a steep slope, so we're way out here, or way out there maybe, and thus it has a strong tendency to drive electrons through an external circuit. So if we're way up here, we can get a lot of power out of this circuit. As we get closer and closer to equilibrium, the electrochemical potential drops, and that means that the power that we're getting out drops, and this is why we call batteries in which that are closer to equilibrium, we call those cells dead. So a reaction that's close to equilibrium has a shallow slope, so we're down in here somewhere, and thus it has a weak tendency to drive electrons through an external circuit. This is not very powerful, and it's not very useful to us as a battery. So remember that the reaction gives energy is related to the composition of a reaction mixture. So we've got this equation. So delta Rg is equal to delta Rg naught plus RT ln Q. So if we can combine these two equations, so this equation and our earlier equation where we introduced the Faraday constant. So now we're replacing delta Rg with the minus VFE cell. So now we get this, and then if we want to solve that for our electrochemical potential, E cell, we now get this equation. And if we combine that first term on the right into our standard cell potential, so we go back, we're combining this term here into our standard cell potential. So here we have the cell potential at some under some conditions. If we want to combine this into a standard chemical potential, a standard electrical potential. So here we have delta GR naught, so we're combining that and divided by VF there. That's a constant. For any one reaction, that value doesn't change. Note that here the Q is going to change and the temperature may be changing, but this value doesn't change. And so we can combine that together into one quantity. And we're calling that our standard cell potential. We can measure these standard cell potentials. Our standard cell potential is the standard reaction gives energy, expressed in terms of potential difference, so that is in volts. So it's basically an equivalent sort of thing here as the standard gives energy. Just now, instead of expressing it in terms of joules per mole, maybe we're expressing it in terms of volts. And now we can get a table full of standard electrochemical cell potentials. So that means that now, when we make that replacement of that first term, now we get the Nernst equation. So now we have E cell equals E cell naught, or standard electrochemical cell potential, standard cell potential, minus RT over VF times the natural log of Q. So in this case, now our cell potential, as predicted by the Nernst equation, is plotted over here. So here we have E cell minus E cell naught. And down here we have log Q. So, and here we have different values for our stoichiometric coefficient E. So, as Q gets larger, or as log Q gets larger, the difference here gets smaller. So note that here, when log Q is 0, if log Q is 0, then the value of Q is 1. And if the value of Q is 1, that means that we have an equal ratio of products and reactants. If Q is larger than 1, then we have more products than reactants. If Q is smaller than 1, then we have more reactants than products. So, the standard cell potential can now be interpreted as the cell potential when all of our reactants and products are in their standard states. So, we have concentrations, or activities, maybe, of our reactants in their standard states are 1. So this means Q has to be equal to 1, and that means that natural log of Q is 0. So that's that 0 point that we were talking about on the last slide. So now let's look at the Nernst equation in a special case of an electrochemical cell that's at equilibrium already. So if our cell is at equilibrium, then Q is equal to K, because K is just a special case of Q once we've reached equilibrium using our equilibrium concentrations or pressures or fugacities. So again, where K is our equilibrium constant here. And a cell that at equilibrium can do no work, and thus means it has a zero potential difference. So that means that the natural log of Q has to be equal to Vf times E naught, V cell naught, divided by RT. So now we can determine that our equilibrium, or we can determine our equilibrium constant of some cell reaction using our standard cell potential. And so now we can just measure the standard cell potential. If we know the temperature and we know how many electrons are being transferred, which should be pretty easy to find out, then we can calculate what our value of K is. And that was equilibrium electrochemistry.